Hello, welcome to my presentation. My name is Kyriakos Alexandros Chondrogiannis, and I am a PhD student at ETH Zurich. Today, I'm going to present you our work with title Vibration Absorption Performance of Metamaterial Lattices consisting of impact dampers. This work is a collaboration with Dr. Tertimanis, Professor Masri, and Professor Hadji. The institutions involved in this project are ETH Zurich and the University of Southern California. The current study focuses on structural response under ground-borne vibration. Waves that are traveling within soil layers can contain various frequency spectra. High-frequency waves can mainly be generated by human activities, such as traffic or railroads, blasting, and machinery operation. On the other hand, earthquake excitation appears to have unique characteristics compared to other types of excitation. Seismic motions are usually composed by low frequency content and can cause great damage on structures. Therefore, vibration mitigation devices for structural protection against low frequency excitation is a crucial element in civil engineering developments. One method of achieving vibration mitigation for structural protection is the use of passive control systems. The most widely known system is the tuned mass damper. It is a linear attachment to a primary oscillator, and the mechanism evolved under dynamic excitation is the transfer of energy from this primary system to the secondary attachment. Under proper adjustment, favorable properties can be observed around the resonance frequency of the protected structure. However, in nearby frequencies, some unfavorable effects can be created, thus resulting to the observation that this system can offer favorable effects under a narrow frequency range. One prospective idea for structural protection is the use of metamaterials. Metamaterials are natural or artificial configurations with extraordinary properties in inhibiting or conditioning wave propagation. They are arranged in repeating patterns of a fundamental construction which is called the unit cell, and periodic arrangement of this fundamental unit cell creates the metamaterial lattice. One of the most important concepts for civil engineering applications is the mass-in-mass concept, where an outer container contains an inner linear oscillator, thus creating the resonator unit cell. Repeating patterns of this fundamental unit cell creates the metamaterial lattice. This metamaterial configuration can be used for structural protection against incoming waves. However, the frequency range within which this metamaterial can be effective, the so-called bandgap, is narrow, and this is limited due to the fact that these resonators are a linear attachment. A very important aspect in the use of metamaterials for structural protection is their coupling with the protected structure. One application is that of the metabarrier, where the metamaterial configuration is not in contact with the structure, but protects a specific region of soil within which the structure is founded. Another implementation is that of the metafoundation, where the metamaterial configuration is in contact with the structure and also supports the weight of it. A third application, which is a hybrid of the previous two, where the metamaterial configuration is in contact with the structure but does not support the weight of it and only constrains it laterally. In our research, the selection of the unit cell has nonlinear behavior, which results from impact phenomena. The unit cell is a single particle impact damper. An outer container contains an inner mass, which is laterally unconstrained and free to impact on the sides. It is useful to understand the behavior of this system under dynamic excitation. Under the consideration of sufficiently small duration of its impact compared to the dynamics of the system, it is reasonable to assume that the displacement of the container and the inner mass immediately after its impact is identical to the ones before the impact. In order to determine the velocities of the two masses after the impact, the deployment of two equations is used. The first is the conservation of momentum, and the second is the definition of the coefficient of restitution, which provides a relation between the relative velocities before and after each impact. The solution of this system of two equations results in the determination of the post-impact velocities of the two impacting masses. The periodic arrangement of elastically connected unit cells of impact dampers results in the formation of the nonlinear metamaterial lattice. Moreover, this lattice is connected to a fixed base on one end and to a primary structure which is subjected to protection on the other end. This lattice has nonlinear and non-smooth behavior which results from impact phenomena. For this configuration, parametric analyses have been performed for varying mass, stiffness, and number of unit cells in order to determine the behavior of the system under varying parameters and also determine the optimal parameters for structural protection. For the simulation of the system, the formation of the equations of motion is required. The system behaves linearly within all time instances that no impacts occur. Therefore, the equations of motion are formed following a linear pattern, provided that the relative displacement of the two impacting masses does not result into impact realization. The formation of the equations of motion for each unit cell is performed, as well as for the primary structure at which an input force is applied. To determine the behavior of the system during time instances when impacts occur, an impact event function should be used. This is deployed whenever an impact is detected at any unit cell, and it provides the post-impact displacement and velocities of its mass. The post-impact displacement are calculated identical as to the ones previous to the impact. As for the post-impact velocities, these can be calculated using the set of equations discussed earlier, including the conservation of momentum and the coefficient of restitution, which results to a linear system of equations, the solution of which results to the post-impact velocities of the two impacting masses of each unit cell. To simulate the response of the system numerically, it is brought into a nonlinear state space form, including the displacement and velocities of each mass. The solution of the system has been performed with the use of the Runge-Kutta numerical scheme. Numerical simulations have been performed for varying parameters of the system. For all analysis, the properties of the primary structure are considered to be fixed. Its mass is equal to unity, its natural frequency is equal to 1 Hz, and its damping ratio is equal to 2%. For all unit cells, the coefficient of restitution is considered to be equal to 0.6, and the free clearance between the outer container and the inner mass is considered to be equal to 0.1. Moreover, no damping is considered in the connection of all unit cells. Finally, an input force is applied at the primary structure, which matches the natural frequency of the structure and has an amplitude equal to unity. For this configuration, parametric analyses have been performed for varying mass and stiffness of the system, as well as the number of unit cells. To understand the behavior of the system, the time history of the relative displacement of the container and the inner mass is plotted for all unit cells. So in this case, 2 unit cells were considered, and we can observe that this value is bounded by the free clearance of the system. Plotting the absolute displacement of the two masses, we can observe that for the inner mass, the displacement follows a linear path within all time instances that no impacts occur. This is a result from the fact that this mass is laterally unconstrained for all these time instances, which results into constant velocity during those time periods. A very important part in the study was the selection of a suitable measure in order to evaluate the performance of the system in vibration mitigation. This was selected to be the energy absorption from the primary system as a result of individual impacts. It was calculated as the ratio between the energy which was dissipated due to all impacts to the total energy which was inserted to the system. In these graphs, the energy absorption ratio is plotted versus varying stiffness in the connection between the unit cells, the mass of the inner particle, as well as the mass of the outer container. Moreover, the number of unit cells that comprise the metamaterial lattice is considered to be a varying parameter. In general, it can be observed that for a higher mass ratio of the unit cell compared to the primary structure, more significant energy dissipation can be achieved for a wider variety of the system's parameters. However, for increasing number of unit cells, a suitable combination of parameters can be detected that can lead to significant energy dissipation even for small mass ratio of the unit cell compared to the primary structure. This is a more realistic situation where the unit cells should have significantly smaller mass compared to the primary structure that needs to be protected. Another observation that can be made is that for low mass ratio between the unit cell and the protected structure, the results in energy dissipation are highly influenced by the stiffness between the connection of the unit cells. For increasing value of this mass ratio, it is observed that the influence of the energy dissipation results is shifted more towards the mass ratio between the inner mass and the outer container of each unit cell. Finally, the behavior of the system has been studied for varying input excitation frequencies. A selection on the system's parameters was made and the time history of the system was recorded. The maximum acceleration of the primary structure was extracted and plotted versus the frequency ratio of this primary oscillator. Additionally, the acceleration amplitude of the linear oscillator has been plotted in order to make a direct comparison of the two graphs. A substantial mitigation of the dynamic load effect on the structure is observed for frequency ratios around the natural frequency of the primary structure. However, taking also into consideration that damping between the unit cells equals to zero, an amplification of the system's response in regions away from the resonance frequency is observed. Moreover, it is observed that an increase in the number of unit cells does not have a notable effect on the attenuation properties of the configuration, especially in higher excitation frequencies. However, a distinctive peak at frequency ratio equal to 0.2 is indicated for the single unit cell lattice, which is not transferred to lattices with higher unit cell number. In conclusion of this study of the impact damper metamaterial lattice, great vibration mitigation potential can be spotted. The reduction of vibration to a protected structure is significant around its resonance frequency. The energy absorption capabilities of the system have been studied, revealing suitable parameters for efficient performance. Finally, the system under investigation produces not only nonlinear but also non-smooth dynamics as a result of impact phenomena, which change the velocities of impacting masses discontinuously. With this, I would like to conclude my presentation. Thank you for your attention, and I would like to note that this project has received funding from the European Union's Horizon 2020 Research and Innovation Programme.